Welcome, science enthusiasts, to a journey into the mind of a true titan, Albert Einstein. Today, we're not just recounting history, we're delving into the very fabric of reality as revolutionized by one man's extraordinary insights. Prepare to explore the cosmos, shrink to the quantum realm, and fundamentally rethink what you know about time, space, and energy. This isn't just about formulas. It's about the profound shift in human understanding that Einstein ignited. Our story begins in Ulm, Germany, 1879, with the birth of a child who would eventually challenge the scientific establishment to its core. From an early age, Einstein displayed a keen curiosity, a relentless desire to understand the underlying mechanisms of the universe. He wasn't a child prodigy in the traditional sense, often struggling with conventional schooling, but his mind was constantly working, grappling with concepts that most adults couldn't even fathom. He famously taught himself calculus at a young age and devoured books on physics and philosophy, laying the groundwork for the revolutionary ideas that would follow. It was this independent spirit, this willingness to question established dogma, that would define his entire career. He wasn't content with merely accepting what was taught. He wanted to know why things were the way they were. This early intellectual hunger, combined with a healthy dose of skepticism, was the fertile ground from which his groundbreaking theories would sprout. We often imagine great scientists as lone geniuses, and while Einstein certainly possessed unparalleled intellect, his journey was also one of continuous learning, questioning, and intellectual sparring with the greatest minds of his time. He was a product of his environment, yet simultaneously transcended it, pushing the boundaries of human knowledge far beyond what anyone thought possible. His early life, seemingly unremarkable to some, was in fact a crucible in which the fires of genius were forged, preparing him for the monumental tasks that lay ahead in reshaping our understanding of the universe. The year 1905, often referred to as Einstein's Annus Mirabilis, or Miracle Year, saw the publication of 4 groundbreaking papers that individually could have secured a Nobel Prize and collectively redefined physics. We're going to dive into the first of these, the paper on the photoelectric effect. Imagine light not just as a wave, as was commonly accepted at the time, but as discrete packets of energy, particles if you will, which Einstein termed quanta, now known as photons. This was a radical departure from classical physics. Previous experiments had shown that shining light on certain metals could eject electrons, a phenomenon called the photoelectric effect. However, classical wave theory couldn't explain some crucial observations. For instance, why did the energy of the ejected electrons depend only on the frequency of the light, not its intensity? And why was there a minimum frequency, a threshold, below which no electrons were emitted, regardless of how bright the light was? Einstein's quantum hypothesis provided an elegant and precise explanation. He proposed that each electron absorbed a single quantum of light. If that quantum had enough energy, i.e., if the light had a high enough frequency, it could knock an electron free. If not, no matter how many low-energy photons hit the metal, no electrons would be released. The intensity of light, in this model, simply determined the number of photons, and thus the number of electrons ejected, but not their individual energies. This revolutionary idea was initially met with skepticism by many physicists who were deeply entrenched in the wave theory of light. However, experimental evidence, particularly from Robert Millikan's meticulous work, eventually confirmed Einstein's predictions, earning him the Nobel Prize in Physics in 1920, Nobel Prize in Physics in 1921. The photoelectric effect isn't just a historical curiosity, it's the fundamental principle behind technologies we use every day, from solar cells that convert sunlight into electricity, to digital cameras that capture light, and even the image sensors in our smartphones. It was a pivotal moment in the development of quantum mechanics, showing that light exhibits both wave-like and particle-like properties, a concept known as wave-particle duality, which continues to be a cornerstone of modern physics. This single paper cracked open the door to an entirely new understanding of the universe at its most fundamental level. Our next stop in 1905 takes us to Einstein's paper on Brownian motion. While it might seem less glamorous than Relativity, this work was equally profound and played a crucial role in validating the existence of atoms and molecules, a concept still debated at the time. Imagine looking at a suspension of pollen grains in water under a microscope. You'd observe them jiggling and darting about randomly, seemingly without cause. This phenomenon, known as Brownian motion, had been observed by botanist Robert Brown in 1827, but its underlying explanation remained a mystery for decades. Classical physics struggled to account for this incessant, erratic movement. Einstein, however, approached the problem with his characteristic ingenuity. He theorized that the visible pollen grains were being constantly bombarded by unseen, incredibly tiny particles, water molecules, which were themselves in constant, random thermal motion. Each collision, individually imperceptible, collectively imparted enough momentum to the larger pollen grains to cause their observed erratic dance. More remarkably, Einstein didn't just propose this explanation. He developed a mathematical model that precisely described the statistical properties of this motion. He derived an equation that linked the observable displacement of the pollen grains to fundamental constants, like Avogadro's number, which relates the number of particles in a mole of a substance, and the size of the water molecules. This was a monumental achievement. For the first time, it provided concrete, quantitative evidence for the existence of atoms and molecules, transforming them from theoretical constructs into verifiable physical entities. Before Einstein, many prominent scientists, including Ernst Mach, were skeptical of atomic theory, considering atoms to be convenient fictions rather than actual physical objects. Einstein's work on Brownian motion provided the irrefutable empirical proof that these tiny building blocks of matter were indeed real. The impact of this discovery extends far beyond just confirming atomic theory. It provided a powerful tool for studying the properties of fluids and the interactions between particles. Today, the principles of Brownian motion are applied in diverse fields, from understanding the diffusion of molecules in biological systems and the movement of pollutants in the atmosphere, to financial models predicting stock price fluctuations, and even the design of nanoscale devices. It demonstrated Einstein's ability to extract profound insights from seemingly simple observations, further solidifying his reputation as a revolutionary thinker. Now, we arrive at arguably Einstein's most famous contribution from 1905, the special theory of relativity. This wasn't just an extension of existing physics, it was a radical overhaul of our fundamental understanding of space and time. Imagine you're on a train moving at a constant speed, and you drop a ball. To you, it falls straight down. But to someone standing on the platform, the ball traces a parabolic path. This concept of relative motion was well understood. However, a major problem arose with light. Experiments, particularly the Michelson-Morley experiment, failed to detect any ether wind, a hypothetical medium through which light was thought to travel. This implied that the speed of light in a vacuum was constant for all observers, regardless of their own motion. This was a direct contradiction to classical mechanics. Einstein's genius was to accept this constancy of the speed of light as a fundamental postulate, along with the principle of relativity. The laws of physics are the same for all observers in uniform motion. From these two seemingly simple postulates, he derived astonishing and counterintuitive consequences. One of the most famous is time dilation. Moving clocks run slower than stationary ones. If you were to travel near the speed of light, time for you would pass more slowly relative to someone on Earth. Another consequence is length contraction. Objects moving at high speeds appear shorter in the direction of motion to a stationary observer. Furthermore, the concept of simultaneity became relative. Events that appear simultaneous to one observer might not be simultaneous to another observer in relative motion. This completely shattered the Newtonian idea of absolute time and space, replacing them with a unified, four-dimensional space-time continuum. The implications were immense. It showed that mass and energy are related, leading to the famous equation E equals mc squared, which we'll discuss next. Special relativity isn't just theoretical. Its effects are observed and accounted for daily in modern technology. For example, GPS satellites, which orbit Earth at high speeds, experience time dilation. Without accounting for these relativistic effects, GPS systems would quickly accumulate errors, rendering them inaccurate. Particle accelerators, where particles are propelled to near light speeds, also provide direct evidence for time dilation and length contraction. The entire framework of modern physics, from cosmology to quantum field theory, is built upon the foundations laid by special relativity, demonstrating its profound and enduring impact on our understanding of the universe. And now, for the crescendo of Einstein's miracle year, the equation that has become synonymous with his genius, E equals mc squared. While often presented as a standalone formula, it was actually a consequence derived from his special theory of relativity, published in a follow-up paper later in 1905. Before Einstein, mass and energy were considered distinct and separate entities, each conserved independently. His equation fundamentally changed this view, demonstrating their equivalence and interconvertibility. Let's break down this iconic formula. E stands for energy, m for mass, and c for the speed of light in a vacuum, which is a very large number, approximately 300,000 kilometers per second, or 186,000 miles per second. The c-squared term means the speed of light multiplied by itself, resulting in an even astronomically larger number. The profound implication of E equals mc squared is that even a tiny amount of mass can be converted into an enormous amount of energy, and vice versa. It reveals that mass is essentially a concentrated form of energy, and energy possesses a certain mass-like quality. Where do we see this in action? The most dramatic and well-known application is in nuclear physics. Nuclear power plants harness the energy released when a small amount of mass is converted into energy during nuclear fission. When uranium or plutonium atoms are split, the total mass of the resulting fragments is slightly less than the original atom. This missing mass isn't lost. It's converted into a tremendous amount of energy, according to E equals mc squared. Similarly, in nuclear fusion, the process that powers our sun and other stars, lighter atomic nuclei combine to form heavier ones, releasing immense energy as a small amount of mass is converted. The sun, for example, converts millions of tons of mass into energy every second, providing the light and heat essential for life on Earth. The equation also tells us that energy can manifest as mass. For instance, in particle accelerators, when particles are smashed together at incredibly high energies, new, more massive particles can be created from the kinetic energy of the colliding particles. Beyond its dramatic applications, E equals mc squared is a cornerstone of our understanding of the universe. It's essential for comprehending stellar evolution, the Big Bang, and the fundamental interactions between particles. It unified two previously distinct concepts, revealing a deeper, more elegant symmetry in nature, and forever altering our perception of matter and energy. While his 1905 papers were revolutionary, Einstein wasn't done reshaping physics. His general theory of relativity, published in 1915, was an even more profound leap, extending his ideas from special relativity to include gravity. Isaac Newton's theory of universal gravitation, while incredibly successful for centuries, described gravity as an instantaneous force acting at a distance. It didn't explain how gravity worked or why objects attracted each other. Einstein's general relativity offered a radically new perspective. He proposed that gravity isn't a force at all, but rather a manifestation of the curvature of spacetime caused by mass and energy. Imagine a stretched rubber sheet. If you place a bowling ball on it, the sheet will sag. Now, if you roll a marble nearby, it won't be pulled by the bowling ball. Instead, it will curve inwards as it rolls across the warped surface of the sheet. In this analogy, the bowling ball represents a massive object like a planet or a star, and the marble represents a smaller object or even light. Massive objects like Earth and the Sun warp the fabric of space-time around them. What we perceive as gravity is simply the motion of objects following the shortest path, a geodesic, through this curved space-time. This elegant theory explained observations that Newton's gravity couldn't. For instance, it precisely accounted for the anomalous precession of Mercury's orbit around the Sun, a long-standing puzzle in astronomy. It also predicted the bending of light by massive objects. During a total solar eclipse in 1919, observations led by Arthur Eddington confirmed that starlight passing near the Sun was indeed deflected by the predicted amount, precisely matching Einstein's calculations. This experimental verification propelled Einstein to global fame. General relativity also predicted the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape, and gravitational waves, ripples in space-time caused by accelerating massive objects. The recent detection of gravitational waves by the LIGO experiment in 2015 provided spectacular confirmation of another one of Einstein's bold predictions, a century after he made it. General relativity is not just a theory, it's the foundation of modern cosmology, used to understand the large-scale structure and evolution of the universe, from the Big Bang to the expansion of the cosmos. It's an unparalleled testament to the power of human intellect to unravel the deepest mysteries of nature. Beyond his groundbreaking theories, Einstein also made significant contributions to our understanding of the quantum world, even though he famously struggled with some of its implications later in his life. We've already touched upon his work on the photoelectric effect, which was a foundational stone for quantum mechanics. Another crucial contribution was his explanation of specific heat capacity, particularly at low temperatures. Classical physics and the equipartition theorem struggled to accurately predict how much heat energy was required to raise the temperature of a solid by a certain amount, especially when temperatures dropped near absolute zero. Einstein, drawing inspiration from Max Planck's earlier work on quantized energy, proposed in 1907 that the vibrations of atoms within a solid, which are responsible for its thermal energy, were also quantized. This meant that atoms couldn't vibrate at just any energy level, but only at discrete, specific energy packets. This simple yet profound idea, known as the Einstein model of specific heat, explained why specific heat capacities decrease rapidly at low temperatures. At low temperatures, there isn't enough thermal energy available to excite the atomic vibrations to even the lowest quantum energy levels, thus reducing the solid's ability to absorb heat. While later refined by Peter Debye, Einstein's model was a crucial step in showing that quantum theory wasn't just applicable to light, but also to matter. It provided compelling evidence that the quantum nature of energy extended to the microscopic world of atoms and solids, further solidifying the nascent field of quantum mechanics. Furthermore, Einstein, along with Satyendra Nath Bose, developed the Bose-Einstein statistics, which describes the behavior of a type of particle called bosons, e.g. photons, helium-4 atoms, at very low temperatures. This led to the prediction of a unique state of matter called the Bose-Einstein condensate, BEC, where a collection of bosons cooled to near absolute zero collapses into the lowest possible quantum state, behaving as a single quantum entity. The BEC was experimentally created in 1995, nearly 70 years after Einstein's prediction, earning a Nobel Prize for the researchers involved. While Einstein famously debated with Niels Bohr about the completeness of quantum mechanics, famously stating, "God does not play dice," his early contributions were absolutely vital in laying the groundwork for this revolutionary field, demonstrating his remarkable versatility and impact across different domains of physics. Einstein's influence wasn't confined to the theoretical realm. His work had profound practical implications, shaping the technological landscape we inhabit today. We've already seen how the photoelectric effect is fundamental to solar cells, digital cameras, and light sensors. Think about the convenience of automatic doors that open as you approach, or the precise exposure control in your smartphone camera. These rely on the principles Einstein elucidated. The E equals mc squared equation, while having destructive applications in atomic bombs, is also the cornerstone of nuclear power, providing a significant portion of the world's electricity. Without understanding the mass energy equivalence, harnessing nuclear energy would be impossible. The energy from nuclear fission provides stable, low-carbon power, crucial in our efforts to combat climate change, though it comes with its own set of challenges regarding waste and safety. Perhaps one of the most pervasive and often overlooked applications of Einstein's relativity is in global positioning systems, GPS. As we discussed, GPS satellites orbit Earth at high speeds, requiring special relativistic corrections for time dilation, and in a weaker gravitational field than on Earth's surface, requiring general relativistic corrections for gravitational time dilation. These relativistic effects cause time to pass differently for the satellites compared to receivers on Earth. Without precisely accounting for these relativistic shifts, a tiny difference of about 38 microseconds per day, GPS navigation systems would accumulate errors of several kilometers per day, rendering them utterly useless for precise positioning. Every time you use a navigation app on your phone, track a package, or even engage in modern air traffic control, you are directly benefiting from Einstein's theories of relativity. His work underpins not just high-tech instruments, but everyday conveniences that we take for granted. Furthermore, his theoretical framework for understanding the behavior of light and matter has guided the development of countless other technologies, from lasers and fiber optics to advanced medical imaging techniques like MRI, which, while not a direct discovery of Einstein, owes its theoretical lineage to the quantum mechanics he helped initiate. Einstein's abstract theoretical physics, initially seeming detached from everyday life, has demonstrably become an indispensable part of our modern technological civilization, illustrating the profound and often delayed impact of fundamental scientific discovery. Beyond the scientific theories and technological applications, Albert Einstein left an indelible mark on the scientific method itself and on the very philosophy of science. His approach to physics was characterized by a profound belief in the underlying simplicity and elegance of nature. He often favored thought experiments, or Gedankenexperimente, as a way to probe fundamental principles, rather than solely relying on complex laboratory setups. These thought experiments, like imagining what it would be like to ride on a beam of light, allowed him to strip away extraneous details and expose the core paradoxes or contradictions in existing theories. This emphasis on conceptual clarity and logical consistency became a hallmark of his work. Einstein also demonstrated the power of theoretical physics to predict entirely new phenomena. His predictions of the bending of light by gravity, the existence of black holes, though he didn't call them that, and gravitational waves, all initially seemed fantastical, yet were later confirmed by observations and experiments, sometimes decades or even a century later. This showcased the immense predictive power of well-constructed theoretical frameworks, guiding experimentalists and observational astronomers toward new discoveries. He championed the idea that the laws of physics should be universal and independent of the observer, a principle that underpinned both his special and general theories of relativity. This pursuit of universal laws, rather than fragmented descriptions, helped unify disparate phenomena under a single, elegant framework. Furthermore, Einstein's famous debates with Niels Bohr and other pioneers of quantum mechanics highlighted fundamental philosophical questions about reality, determinism, and the role of the observer in physics. While he never fully accepted the probabilistic nature of quantum mechanics, God does not play dice. His resistance forced quantum physicists to rigorously defend and refine their interpretations, ultimately strengthening the field. His intellectual independence, his willingness to challenge established dogma, and his relentless pursuit of deeper understanding continue to inspire scientists today. He wasn't afraid to be wrong, to question, and to push the boundaries of human knowledge, leaving a legacy that extends far beyond specific equations to a fundamental approach to scientific inquiry and a testament to the human capacity for profound thought. The enduring legacy of Albert Einstein is a multifaceted one, extending far beyond the pages of physics textbooks. His theories have become so fundamental to our understanding of the universe that they are now woven into the fabric of modern science and technology, influencing fields from cosmology and astrophysics to everyday engineering. His work continues to be a cornerstone for new research, inspiring generations of scientists to probe deeper into the mysteries of space, time, matter, and energy. Researchers today still grapple with the grand challenge of unifying general relativity with quantum mechanics, Einstein's theories describing the very large and the very small, respectively. This pursuit of a theory of everything is a direct continuation of Einstein's quest for a unified description of nature. The study of black holes, gravitational waves, and the early universe are all vibrant areas of research that owe their existence to Einstein's theoretical foresight. Furthermore, his influence transcends the scientific community. Einstein became a cultural icon, symbolizing genius, intellect, and humanitarianism. His distinctive appearance, his witty quotes, and his thoughtful pronouncements on peace, politics, and education made him one of the most recognizable figures of the 20th century. He used his immense fame to advocate for global peace, disarmament, and civil rights, demonstrating that scientific brilliance could be coupled with a strong moral compass. His unwavering commitment to truth and reason, even when it meant challenging the status quo, serves as a powerful reminder of the importance of intellectual independence and critical thinking. The image of Einstein sticking out his tongue, a playful defiance of convention, perfectly encapsulates his spirit. He taught us that imagination is often more important than knowledge, encouraging us to think creatively and question assumptions. In a world increasingly shaped by scientific and technological advancements, Einstein's legacy reminds us of the profound impact a single individual can have on human civilization, not just through their discoveries, but through their enduring spirit of inquiry and their commitment to a better world. His name will forever be synonymous with genius, a beacon of intellectual curiosity, and a testament to humanity's boundless potential to understand the universe. And so, we conclude our exploration of Albert Einstein's monumental contributions. From the quantum leaps of the photoelectric effect and the atomic revelations of Brownian motion, to the mind-bending concepts of special and general relativity, and the iconic energy-mass equivalence, E equals mc squared, Einstein didn't just add to our scientific knowledge, he fundamentally reshaped it. He showed us that time isn't absolute, space isn't merely a backdrop, and gravity isn't a force, but a curvature in the very fabric of existence. His legacy is not just a collection of equations, but a new way of looking at the universe, a testament to the power of human thought and imagination. We use his discoveries every single day, from the GPS in our cars to the nuclear power that lights our cities, and the very way we conceptualize the cosmos. Einstein's work underscores a crucial lesson in science, that challenging assumptions and daring to think differently can unlock profound truths. He wasn't afraid to question centuries-old paradigms, and in doing so, he opened entirely new avenues of inquiry that continue to drive scientific research today. The quest for a unified theory, the exploration of quantum gravity, and the search for answers to the universe's biggest questions are all echoes of Einstein's own intellectual journey. He reminds us that the universe is far more wondrous and complex than we can ever imagine, and that the pursuit of knowledge is an endless, thrilling adventure. His life and work are an enduring inspiration, not just for scientists, but for anyone who seeks to understand, to innovate, and to make a lasting impact on the world. The universe, through Einstein's eyes, became a place of deeper mystery and greater elegance, a canvas waiting for curious minds to continue painting its intricate details. His story is a powerful reminder that true genius lies not just in finding answers, but in asking the right questions, and in doing so, reshaping our perception of reality itself. Thank you for joining us on this extraordinary journey through the mind and discoveries of Albert Einstein. If you enjoyed this deep dive, please like, share, and subscribe for more scientific explorations. Until next time, keep exploring, keep questioning, and keep wondering about the incredible universe we inhabit.